Welcome to the lecture of Digital Signal Processing. I am Kanagavalli, Assistant Professor in the Department of ECE at Bank Institute of Higher Education and Research. Today's topic is multi-rate digital signal processing. It is a presentation outline. First, we'll discuss about introduction to multi-rate digital signal processing. Then, we'll say about what is decimation. Next, we'll say about what is the interpolation. Then, we'll say about sampling rate reduction by integer factor b. Then, sampling rate increase by integer factor l. Then, sampling rate conversion by integer rational factor l by d. Next, we'll discuss about polyphase filters. Then, last topic is applications of multi-rate digital signal processing. The systems that employ multiple sampling rates in the processing of digital signals are called as the multi-rate digital signal processing. These multi-rate systems are sometimes used for sampling rate conversion. In most of the applications, some multi-rate systems are used to improve the performance, or it is used in order to increase the computational efficiency of the system. The basic sampling operations in a multi-rate system are decimation and interpolation. The term decimation means decreasing the sampling rate of signal, whereas the term interpolation means increasing the sampling rate of the signal. Next is sampling rate reduction by the integer factor b. In the sampling rate reduction, we have the decimation involves two stages or two steps. One is that it includes the anti-aliasing filter followed by the downsampler. Now the decimation by a factor of b, where this b is a positive integer that can be performed as a two-step process, and which consists of the anti-aliasing filter, which is represented by h of n, followed by an operation known as a downsampling, and this operation is performed by the downsampler, which is represented by a downward arrow mark as a letter b. In decimation, the sampling rate is reduced from fx to fx by b. So for a discrete time signal, which is given as an input to an anti-aliasing filter x of n, for that the sampling rate is fx. This sampling rate is reduced the output into fx by b by discarding the d minus 1 sample for every d sample in the original sequence. So it is a representation of a decimated equation, and this is a block diagram representation of the decimation. Let's see the example for the sampling rate reduction by integer factor b. Here the factor integer is taken as 3. The input sequence is given as x of n. From the input sequence x of n, after decimation, we'll get the output y of n as the. Since here the sampling rate gets reduced by the factor 3. This is the problem for the sampling rate reduction by integer factor b. The sampling rate of a signal x of n is to be reduced by decimation from 96 kHz to 1 kHz. The highest frequency of interest after decimation is 450 Hz. Assume that an optional FIR filter is to be used with an overall passband ripple of 0.01 and a passband deviation are stop band ripple with 0.001. From the given specification, we need to design an efficient decimeter. Let us see the solution for this problem. In order to find the efficient decimeter, taking the values for we take 4 different values for I 1 to 4. After taking this value, we can compare the design. On comparing from that, we will select the best design of the decimeter. So first, we are going to consider one stage design. For that, I will be 1. So it is a block diagram for the one stage decimeter. It includes the low pass filter followed by the decimeter. Here 96 kilohertz gets downsample into 1 kilohertz. Here we are using a low pass filter. So it is a representation of low pass filter that allows only the low frequency signals to pass through and blocks all the high frequency components. Similarly, when I equal to 2 in the two-stage design, having two factors, M1 is taken as 32 and M2 is taken as 3. So in this two-stage system, at the first stage, the sampling rate is reduced from 32 kilohertz to 3 kilohertz. In the second stage, from 3 kilohertz, it is reduced to 1 kilohertz. So in the first stage, 32 is converted to 3 kilohertz. Next, and then 3 kilohertz is converted to 1 kilohertz. So here the sampling frequency is fs is reduced to 1 kilohertz. Then here the pass band ripple is given as 0.01 and stop band ripple is 0.001. Filter length is given as 4881 and transition width is given as 5.208 into 10 power minus 4. Similarly, for two-stage decimeter, we get the stage 1 frequency has stage 1 sampling frequency has 2500 Hz and stage 2 frequency has 500 Hz and transition width for the stage 1 and stage 2 is obtained. Similarly, the length of the filter for the stage 1 and stage 2 with pass band ripples are obtained. So this is how a efficient decimeter is designed using the given specifications. If the sampling rate gets increased by an integer factor L. Interpolation by a factor of L, where L is a positive integer that can be realized as a two-step process. The first step is of performing upsampling and second step which is followed by the anti-imaging filter. This anti-imaging filter is usually a low-pass filter is used. This upsampler also called as a sample rate expander. And this sampling in the decimeter, the sampling rate gets reduced, whereas here the sampling rate gets multiplied by the factor L. Upsampling operation to a discrete signal x of n, it produces an upsampled signal y of m according to the relation. So it is the equation for defining the interpolation, and it is the representation of the block diagram of interpolation. This upper arrow mark with the integer L, it represents it is the with the upper arrow mark with the L, it represents it is the interpolator. For this input is a discrete signal x of n and output is y of m. It is easy. For this y of m, if we represent this output in a Fourier transform, so if the above output of from the anti-imaging filter is the expressed in terms of the frequency domain, then we'll get y of m as y of equal j omega t. It is equal to x of equal j omega t l. So the first waveform implies that the original sequence, and second one implies the intermediate sequence, and the last one implies that the output sequence. So before we have seen the example problem for the decimator, next now we'll see an example problem for an interpolator. Here a digital audio system exploits oversampling techniques to relax the requirements of the analog anti-imaging filter. The overall filter specification for the system is given below. The baseband or the method frequency is given as 0 to 20 kHz, and input sampling frequency fs is given as 44.1 kHz, and output sampling frequency is given as 176.4 kHz. Then stopband attenuation is 50 decibel and passband ripple is 0.5 decibel. The transition width is 2 kHz. Then stopband edge frequency is given as 22.05 kHz. So in this given filter specification, we need to design a suitable interpolator. So here also we are having a single stage and a two stage interpolator. It is this block diagram as a representation for a two stage interpolator. In the number of stages 1, then interpolation factor L will be 4. In that case, the filter length will be 146, and normalized transition with del F is given as 0.04535, and the passband stopband values are 0.03925 and 0.00313. Here we have the example for two-stage interpolator. Here the number of stages is 2, and also the interpolation factor L is also 2. So 2 times we are having an upsampler by factor 2. Then the filter length is 1 time we are having filter length as 6, and another time the length of the filter is 83. So the transition width is calculated for the stage 1, and transition width for stage 2 is calculated. Next, the sampling rate conversion by integer rational factor L by D. The sampling rate conversion by a rational factor L by D, it can be achieved by first performing the interpolation by the factor L, and then decimation the interpolated output by a factor D. So first we are doing the interpolation of the factor L. After this interpolation output is then decimated. So in this process, both the interpolator as well as the decimator are cascaded together. A common use of a multi-rate signal processing is for sampling rate conversion. Suppose a discrete signal x of n is sampled at an interval t1. Then we wish to obtain a signal y of n that is sampled at an interval t2. Then a technique of decimation and interpolation enable this operation, so that providing the ratio t1 by t2 is a rational number. That introduction can be accomplished by a L-fold expansion with upsampling followed by the low-pass filtering and the M-fold decimation. It is important to emphasize that the interpolation should be performed first and the decimation should be performed second in order to preserve the distinct spectral characteristics of the exopium. Furthermore, by cascading the two in this manner, both of the filters can be combined into one single low-pass filter. This is the example. So here consider a multi-rate signal processing problem. First condition is state with the help of a block diagram that process of changing a sampling rate by a non-integer factor. We need to develop an expression for the output y of n as a function of the input x of n for a multi-rate structure for a given figure. So first, we need to perform an upsampling process by a factor of L following of the interpolation filter section of I. After the interpolation filter, we need to continue the output from that filter through an anti-aliasing filter and finally operate the downsampling. So it is a sampling rate conversion by integer rational factor L by D. So first the discrete signal x of n is then first upsampled by 5, then followed by downsampled by the factor 10, and again this upsampling are by the interpolator value 2. So here the output y of n is equal to x of n for n is 2r. In all other cases, the value will be 0. That's the polyphase filter. It is a very useful tool in a multi-rate signal processing. It is so-called polyphase representation of signals, and that system facilitates the considerable simplification of the theoretical results as well as an efficient implementation of a multi-rate system. The formally defined in an linear time invariant system can be considered with a transfer function h of z. So here a linear time invariant system is considered. Here the transfer function is obtained as h of z, which is given by summation n varies from minus infinity to plus infinity h of n z per minus n. So this type of structure is very inefficient owing to the interpolation process, which introduces the L-1 zeros between the consecutive points in the signal. For example, if L is large, this upsampling value is large, then the majority of the signal components are fed into the FR filter of 0. So as a result, most of the multiplications and additions are 0, that is, many pointless calculations. Furthermore, the decimation process itself implies that only one of every m output sample is required at the output of the sampling rate converter. And consequently, only one out of every m possible values at the output of the filter needs to be computed. And this type of structure, therefore, it leads to much inefficiency during the process of the rate conversion. So a more efficient realization structure of the sampling rate converter, it uses the polyphase filters. And this polyphase filter is taken into account that after the interpolation process, the signal consists of L-1 zero coefficients, and the decimation process implies that only one out of every m number of samples is required at the output of the converter. To make the scheme more efficient, the replaced by a bank of filters. That is a polycrate filters that are arranged in a parallel way so that we can attain the efficient realization. Here the sampling rate conversion process is then undertaken by the multiplexer at the output by selecting every M into C factor M into C by L samples. This is about design and implementation of a polyphase filter. This is structure for a sampling rate conversion. So in terms of the parallelly we have in parallelly means filters are low pass, that is the interpreted filters are connected. Here the sampling rate conversion, which is interpolation or decimation, is also performed by means of a polyphase filter structure. By this, we can attain a better computation efficiency when compared to the FAR system. Let us see the application of multi-rate digital signal processing. Here the multi-rate system, here we can see the block diagram representation of a digital to analog conversion for a CD player using a 8 factor 8 over sampling. And then a multi-rate system that are used in a CD player when the music signal is converted from digital into an analog form. Here the digital data of 16-bit word are read from a disk at a sampling rate of 44.1 kHz. Then, if the data were converted directly into analog signal means, then image frequency bands that are centered on a multiples of a sampling rate would occur, which causes the amplifier to be overload. So that distortion may occur in a music signal. In order to protect against this distortion, a common technique called as the oversampling. So here we have a common technique called as the oversampling is often implemented nowadays in all the CD players and in most digital processing systems of the music signal. So it is customary to oversample the digital signal by a factor of 8 followed by an interpolation filter. The digital filter contains the interpolation filter in order to remove the image frequencies. Here the sampling rate of the signal is now increased up to 352.8 kHz. This digital signal is converted into the analog signal by a D to A converter, and this signal before digital speaker, it is then passes through the low pass filter. Let us see the application of multi-rate digital signal processing for a above CD plane example. Here the figure A, it illustrates the 20 kHz sinusoidal signal after the samples at 44.1 kHz. It is denoted by X of n. Here we have 6 samples, 1, 2, 3, 4, 5 and 6. 6 samples over a period of 2. So here we have one period and here we have another period. So we have 2 periods here. So if a signal X of n was converted directly into analog waveform, then it would be very difficult to exactly reconstruct or retrieve that original signal back. So that next we are performing an interpolation by using an interpolated by a factor of 8. After interpolation, the figure C, it shows the analog signal y of t, it is y of t, that is reconstructed from this digital signal y of n by passing it to the digital to analog converter. Then finally, the figure D shows the waveform of the Z of t, which is this Z of t is obtained by passing the signal passing the signal Y of t through an analog low pass filter. After that, we'll get this final set of t. Then the effect of the oversampling also has some other desirable features. Firstly, it caused the image frequencies to be much higher and therefore it is easier to filter out. And secondly, it reduces the noise power spectral density by spreading the noise power over a larger bandwidth. Here the noise power spectral density is given as the ratio of total power by the bandwidth. So these are the applications of the multi-rate DSP.